much, Mr. Chairman, and good afternoon. I will focus my presentation in high cycle fatigue and plane specimens. We can divide the materials between ductile materials and fragile materials, and if we analyze the crack direction during the stage 1, during the initiation, it's generally assumed that for ductile materials this direction is the mode 1 direction. That would be the shear stress or maximum tangential stress direction. While if you have a fragile material, the crack during this initiation will coincide with the maximum normal stress direction. It is known as mode 1. In high cycle fatigue, to decide if you have a ductile or a fragile material, a reasonable way is to study the fatigue limits in tension and torsion test, and to make the ratio. That ratio is close to 0.5. That means that the fatigue process is shear dominated. So if this ratio is close to 1, that would be dominated by tensile, so that would be a fragile material. From these statements, some questions arise. First one, what happened with semi-ductile or semi-fragile materials? Thinking about the ratio, if we have a material with a ratio of 0.75, for example. And the second question is that there are materials which may have a stage 1 in a mixed mode, or mode 1, mode 2 combined. So we have decided to make a campaign of tests to try to answer these questions. So in this presentation, I will show the first material we have studied. So we have studied austenitic stainless steel. These are the static properties, the monotonic properties. Just to see that the elongation is very high, 56% after the break. About the microstructure is made mainly of austenitic grains with some delta ferrite bands, mainly austenitic grains. And the mean size of these grains is 80 microns. About the fatigue test, we did fully reversed test in tension, in torsion, and in phase tension torsion. The specimens are cylindrical with a central diameter of 12.5 millimeters. The carefully polished the specimens, hydraulic machine, and the runout was 3.5 million cycles. So these are the S and curves for the push-pull test and the torsion test. The most remarkable feature is that the lines are very horizontal, which means that the calculation of the fatigue limit has a little uncertainty. So we got these two fatigue limits in tension and torsion. We made the ratio, and it's 0.91, which is close to 1 and which is close to a fragile material. Just to remind that, however, in the monotonic behavior was very ductile. These are the curves for the biaxial test. The first one is the maximum shear applied stress is half the normal applied stress, then sigma equal to top, and then more torsion, 2 sigma equal to top, more torsion here, and the last one was the full torsion. So in this graph, we have plotted the 6 fatigue limits in sigma to graph, and we can see that we can fit this experimental data better with an ellipse quadrant. instead of an ellipse arc. Well, just to say that literature assume that this material should be better treated with an ellipse arc as it is fragile, as we check the results of Goff, the classical work of Goff. I would say that the fragile materials he studied were just cast irons, and not stainless steels or more modern materials. So that probably is the reason why there is that contradiction between these results and the classical results. So the main objective of the work, which is the crack direction during the initiation. So in the plot we show how we are going to measure this angle with this direction with an angle called alpha, which is the angle of the crack direction related to the horizontal axis x, which is in the cross section, while the y-axis is along the longitudinal of the specimen. We will use a second angle as well. We will call it theta, which will be the angle of the crack forms with the first principal stress direction. We will use it because for the comparison with the models. Of course, this first principal stress direction will change with the tests. Will be 0, or with the x-axis for a tensile test will be 45 for a torsion test. So how we measure this alpha, this initiation angle in our tests? Well, this is an example. This is a broken specimen, a fatigue tensile test, fully reversed, was 145,000 cycles. And in the second picture, we see the fracture surface, and we have analyzed it optically in an electron microscope. And we see that the lines that radiating from its zone or pointing to an area, and we consider that that zone will be the initiation. That initiation will be along the surface, in this case measures 750 microns. So we go back to the surface of the specimen and we make pictures along the crack, and we observe carefully that 750 microns, and we measure the angle. In this case, this angle will be 12 degrees, and because the size of this zone is around 10 grains, we consider that it is stage 1. This is another example with a non-broken specimen, because when you do some torsion, it's not possible to get broken in two, because you would need to twist to match the specimen. You are not able to machine it. So but the crack is quite long, 17 millimeters. So the third picture shows all that crack along the surface, which is made of 20 or 30 pictures carefully joined. And then we go back to the fracture surface, which could be the second picture, and we observe the initiation, and it's at the top, in the weight zone, and this time measures 1,450 microns. So we do a zoom in the crack along the surface, we measure the angle, and now it will be an angle of 37 degrees. Different. So we have done this for 20 tests, all of them in high cycle fatigue, which for us was more than 10 to the power 5 cycles. And I have divided it in, I only put the initiation zone, not the full crack, just to focus. And these are the push-pull tests, which angles around 5 to 10 degrees, the angle alpha. If we increase the torsion, that's the second group of tests. We increase the angle alpha close to 20. More torsion, that is sigma equal to tau, will be around 30. This is to more torsion double than sigma. The angles keep growing to almost 40. And finally, torsion, pure torsion angles around 40 degrees. So we have decided as well to compare with models, in models of crack direction in high cycle fatigue. For them, we use this theta angle, again, the first principal stress, but it's easy to calculate the angle theta or alpha related. So we have chosen the Matake and Margarian model, which is, it says that the angle will be theta equal to 45, which is shear model, pure mode 2. And then two models, the Carpinteri and Spagnoli and Charles and workers. The angle depends on the material, depends on the particular distribution of torsion. And the prediction would be theta equals to 11, and for the last one, 17. So we have plotted the experimental angles theta, and which are all the 20 dots, or all the tests, and in line the predictions. Well, the 20 experimental tests will give you a mean value of theta equal to 3.5, which is close to 0, which is close to mode 1. Matake will say 45 degrees, mode 2 will be very far, and the best prediction will be for Carpinteri. So, just some conclusions. I would say that, to summarize that, this material behaves as fragile in fatigue, while it behaves very ductile in monotonic. So I wonder if, or I wouldn't recommend to correlate static properties and high cycle fatigue properties for this material, and probably for others. And crack initiation deviation goes in mode 1. So going back to the two questions I did at the beginning, what happened with semi-ductile materials, and it's possible to get a mixed mode, we still don't have the answer. We need to do more tests and be lucky and get materials with this ratio close to 0.75. We don't know from the beginning. That's all. Thank you.